Get going. So, so the plan for today, I want to quickly, we want to finish the overview of the isolation mechanisms that we talked about last week. In particular, the way I want to finish it is to illustrate how they all sort of fit together in XV6 by looking at the first system call. So starting the first address space, the first context switch, and then the first system call. I'll do that first. Then after that, we're going to focus in on one of these isolation mechanisms, namely address spaces. We talked a little bit about it last week. But now we're going to sort of fill in the details. In particular, we're going to look at exactly how the x86 can be programmed to provide address spaces. And, some of you recently have started to struggle with that in the latter part of Lot 2, and so hopefully a lot of the things that are either going to be hopefully going to be useful to you, sort of either reinforce what you already understand or help you along in Lot 2. Okay. So, so I'm back here at user init, where this is the kernel allocated some memory, set up a kernel page table, and then does a whole bunch of other stuff, and at the end of it, it actually calls user init to create the first user process. And mostly that user process is a trampoline to get sort of going and actually fork off a shell at some point. And the way, so quickly sort of running through again, what happens, the first thing the user init does is actually allocating a proc structure. And so for every process, for every process x86, there's a proc structure. And just to remind you quickly what it looks like, it has a page directory, but it's not filled in. It has a kernel stack. We will talk a little bit about it. Its state, process ID, and name, et cetera, et cetera. And we're going to fill that out and then get going. In Josh, we typically don't call it the process structure or proc structure, but we have to call it the environment. Mostly because to differentiate the fact that in the process structure in XV6, there's a lot more information that is used to implement system calls, the Unix system calls, while in Josh, the kernel doesn't really know about system calls, Unix system calls at all. And so the proc structure is much more slimmer, and therefore we call it an environment. But basically, they're referring to the same concept. Okay? So the set of KVM, allocates a page directory for the kernel and then initializes that. Init UVM takes this little piece of code that's sitting somewhere in physical memory and maps it as the first page of the user process. And I'll talk a little bit more about that in detail. And these are just a minimal set of instructions. In fact, if you're, we can look at it in the code. It's a tiny little program just to get off the ground. And in fact, the program in total is this, 5 instructions. And the only thing the program really does, if you sort of look carefully, it actually does an exec call, an exec system call. Right? In fact, and the arguments of exec are below. It actually tries to exec the program in it. And presumably init is a much bigger program that's stored somewhere in the file system and that has a lot of different features. Okay, so this is a little bootstrap program to get off the ground. So it's like 5 instructions. And so, not surprisingly, we allocate only one page for those 5 instructions, and with a little bit of data, stick it in the, map it into the virtual memory, and then we initialize the track frame. So this has to do with the stack that we're trying to set up. So this process, when we return to use space, that process needs to have its own stack. And the stack is necessary so that we can do time slicing between different programs. Remember, the whole point, if we want to switch from one process to another process, we need to sort of save that process on the site and then restore it with new information that we're going to load in the processor. And what this code does is setting up a stack so that later on, when we do switch, everything will work out. And the context switch will work out. In particular, the stack has a couple pieces of information on it. It has a track frame, which is the information that the process stores when it actually makes a system call from user space to kernel space. So the process dumps a whole bunch of state on the current running stack. So that's going to be sitting here. We're going to set it carefully up as if we were a call from user space. And the reason we do that is because we want to return to user space. And so it makes, we can use the same code path that we already have, or that we'll see later in the kernel, to actually go from kernel space to user space. So we're going to set up some track frame. There's a couple of functions that we're going to be filled in, return addresses, so there's going to be on the stack a track return address, and there's also going to be a context, which is basically the context that we're going to use to switch from one thread to the next thread. So in fact, what we're going to do, sort of the current processor is running on the stack that we set up during booting, and what we're going to do at some point is switch from that stack to this stack, and we're going to pop up all the context information from that stack into the processor so that that actually makes the context switch happen. Right? So it sounds a little bit abstract, but we'll see in a second how it all works out. Okay, so then the next statement actually fills in, the next set of statements fills in the trap ring. And so last time, and so basically what it does is just initializes whatever particular fields here on the stack so that they later are going to be pushed in the right places. And one of the things it fills in is this code segment selector. And the reason, of course, is that at some point when we go to user space, we need to load the new code segment selector into the processor because the code segment selector has in its bottom 2 bits the user privileges. In fact, I said this wrong last time. Somebody caught me on this, and then I did some hand-wavy thing. Where it works out. It sort of works out. So I pointed to the 3 here, correct, as the user level privilege. That's not true. The user level privilege is this, which also happens to be 3. If you look in the defined statements I think in the MMU.h. Okay, so just 2 3s here instead of 1, and neither one I can pronounce correctly. Okay, so it fills in a bunch of the code segment selector. I'll talk a little bit more about it in 5 to 10 minutes. Sets the data segment selector up. Then it initializes a bunch of other things we really care about. It sets the page, the stack pointer. So that now the stack pointer in the trap frame is going to be pointing where? Some stack pointer in the trap frame. Where is that pointing to? Anybody?
Very end of the allocation space. So when it says space, it says the page size. It's set to the limit.
Yeah, what's page size? How big is page size?
4K.
4K. So it actually sets it to 4K, 496. The intention, of course, is that when the process is going to switch, here's this 1 page of code that we have, right, where init code is located. In fact, what it looks like, when the top of that init code actually has a stack. So that's where the user stack is going to live. So we have 2 stacks. One is a user stack, and the other one is a kernel stack. So every process has 2 stacks. And so this is setting up the user stack part. And then the next instruction sets the EIP to 0. Where the idea here is that the address 0 is the first address that's going to point to the first instruction of init code. Okay, so we're hoping to return to user space with the stack pointer set to 4K, 496, and the EIP to set to 0. So this is all prep work, correct? We're just setting things up, appropriately, so that when we're actually things go in motion, that everything ends up in the right place, and we do have end up user space at instruction 0. All right. This is just for debugging purposes, and now we have a complete process structure filled in. You can see that the name is init code. It's runnable now, and it has a page directory, so everything's sort of filled in, set up, to actually start using it. All right, so now we want to see actually what happens. It's a little bit tricky because we're basically told the kernel you can run this process, and so there's an whole other part of the kernel that is sort of in charge of figuring out which runnable processes to select. That piece of code is the scheduler, so I'm going to set this breakpoint in the scheduler. And I'm just going to run continue and then hope that the scheduler actually will invoke. And that should be the case. Here we go. I'm just going to walk through the scheduler. It's pretty, actually for now, not so exciting. We'll look at it in much more detail later. So it selects a process to run, and let's see what actually process it actually selected. So it actually selected our init code, you can see, which is not surprising, correct? Because how many runnable processors are there in the system at this point? 1. So glad it found that one. So it sets it actually to running, and now sort of exciting stuff is going to happen. We're going to switch. So we're going to switch from the stack that we're currently running on, which is just that kernel stack that we set up earlier when doing booting, to this kernel stack for the user process. So we're not switching to user space yet. We're just switching from one stack in the kernel to another stack in the kernel. And this has to do, the reason that every process has its own kernel stack, has to do with the fact that we actually do take interrupts in the x86 kernel. So for example, in Josh, you're actually going to have in total one stack in the kernel, well, two, one per processor instead of one processor. Okay? So let's see actually what happens. So notice it has two arguments, right, that is passed in. One is the CPU scheduler, which is basically a pointer to the context, where the context of the current processor, where the state, is a pointer to the context where the state of the processor, as it's currently holding, is going to be saved in. And then we're going to restore from the proc context, which is that context we just filled in. So we're going to save one and load the other one into the processor. So let's see how that happens. And this will look a little bit like magic, but later in the semester we'll talk much more about it in detail. But I want to give you some sense of what happens. So the first thing done are the two arguments are stored in registers. The first argument in EAX, right? This is where we need to store into. And then the other one where we load from is stored in EDX. So first is the saving happening. So the processor state is sort of loaded out of the processor and into this context. And there's not that much actually to save. We found that pushes the EBP, so that's being saved now. That's the EBX is saved, ESI is saved, a couple more things. And then the interesting stuff, now we're going to have to switch, we save the stack pointer, and, wait, I'm disconnected, here. And then actually we're going to switch stack pointers. So let's look at this. So now we switch stack pointers and we're pointing to something completely different, right? Because we loaded this from EDX, we put it into ASP. So basically our stack pointer should be pointing to wherever key context was pointing to. Right, so if we print the values out here, hopefully we'll recognize some things that actually are not loaded on the stack. Right, so let's print out a couple things. $ESP, and we'll see there's a whole bunch of values on the stack, correct? And one of them a bunch of zeros, not surprising, correct? Because remember we set a lot of things to zero. And there's one just for ADC, correct? Or this thing that it must be the EIP, correct? So let's double check that that's the case by printing out what the address is of the fork return. See, it's exactly, yeah, it's the right address. Right? So now we switch a stack pointer to basically point to exactly here. Right? Clearly, the goal now is to switch, is to load all the stuff into the processor, and then return from this context switch return, and then we should end up on the new processor's kernel stack at some place. So let's do that. Boom, we pop in stuff from the stack, correct? It's all restoring, loading stuff from the stack into the processor, popping EBP, and now we're going to return. So what is return going to do? Well, return is going to pick up this thing that we saved, correct, and put it in the EIP. And so with a bit of luck, we're going to end up in fork return, right? Make sense? So now we're off, the kernel stack. We're into the kernels. We're off the boot stack, and we're now off on the kernel stack in a proc, and we're running on that. Right? And most of the stuff is now gone. Right? We're basically here. Make sense? Yeah.
So all these kernel stacks are in the top half of the memory, so we don't need to worry about what we're using.
Yeah, they're sitting somewhere. Of course, all the kernel runs in the bottom, in the top half of the address space. Right? And so somewhere we allocated some page for the kernel stack. In fact, there are many kernel stacks allocated. Right? For every process, there's going to be some page that refers to some kernel stack. And so there's nothing else than like whatever 4K or bytes of memory. Make sense? And if proc alloc or alloc proc was the place where we allocated that kernel stack. Some good questions. Okay, good. So let's see what happens next. Now, by keeping going, we'll talk about locks later. It actually checks if this is the first process, and in this case, it's true. And the reason we're doing that is because we need to initialize some stuff that we're going to talk about later, so we don't really care about it right now. And boom, that's all. Now we're going to return again. Right? So where are we going to return to? What's the next instruction where we're going to end up?
also
Sorry?
in the new process?
No, not yet.
Track very much.
We're going to return from track. We're going to go to track return. Right? And the reason we're doing that is because we simulate it as if we entered the kernel. So let's see if this is true. Boom. And we are in track return. And so what is track return going to do? Well, it's going to restore, basically. It's going to set up, to return to user space. So it's going to save, it's going to restore all the registers that the user space code was using. Well, in this case, there was nothing that the user space was using because we haven't run it yet, but in the normal case, this is exactly what would happen. Right? So we're going to, so the first thing is pop out, which pops up a whole bunch of registers. GS, FS, all the selectors, DS, and then it actually pops up some more stuff. So let's now print out, see if that actually works out. 10x you see there's a couple more things in the stack, not much. What is this 100? You guys see?
ESP.
That's the ESP, correct? And we're going to load that. And the idea was that basically we jumped from user space into kernel space with the ESP set to 4K, and we're now restoring it. Except that we never jumped in, but we're just simulating it, right? And so, what did you guess that this is? I'm guessing actually, well, one of them is going to be the EIP, correct, which is going to be 0. And what is this? The 2.3 and the 2P. I guess what the 2.3 is. Ends in a 3. I'll give you that. Yes, sir? Yeah, it's a code selector, correct? So basically what IRED does, remember that IRED actually pops off both the code selector and the offset, which is the EIP, into the process, an atomic operation, right? And this is crucial for security that actually happens. So let's see if this, so presumably we're going to be very close to the big moment where we're going to go to user space, right? So let's go, and boom, there we are. Right? So there's a couple things to note here. We are executing at address 0, virtual address 0, correct? Not physical, which corresponds to basically, we're sitting out here with a page table set up appropriately, and presumably we're running some instruction, the first instruction in a code. Right? In fact, we can see what the first instruction is. It's a push instruction. And remember, if I think just to prove that it's true, hopefully it starts with a push. Okay? It starts with a push long. So it's definitely the same code. All right. So in fact, we can look at the four instructions. So 0. So here are the 4 instructions. Actually, let me. So you see the 2 pushes, correct? Or 3 pushes to move, which is the move from 7 into the AAX, and then the int instruction. So what's going on here? What's giving you your homework? You did. Any guesses what this all is about? What is 7?
Syscall number?
Yeah, it's a syscall number probably, yes. And we probably look up in syscall.h or whatever in syscall.c. Anybody remember what 7 is? Exec. Yeah, so this is going to be exec. These are presumably arguments to the exec, correct? Addresses that, where pointers are stored to the string in it. And then trap, what is this trap? This number?
Syscall.
Sorry?
It's the syscall interrupt.
Yeah, it's a syscall interrupt, basically, right? So this is all so we can, unfortunately, I can't sort of single step through this right now because of the way things are set up, because this is not a piece of code that was compiled using stabs and debugging information at all, right? This is a bunch of instructions that were just moved and copied literally into memory, and we're just executing them. But where we're going to end up when we execute this piece of code? In trap, right? So let's do a double check. So we'll set a big for any trap, and we'll continue random trap. Let's see what actually happens. So the first thing you do is check if it's a system call, right? Like there. So apparently it's a system call. Proc is not killed, and so we're back in, and we actually have a trap frame again. So actually we can do print trap frame. Oops, I always do that. You'll see that here's the trap frame, which was a Now, this is the same track frame as before, right? We had to set pointed to it, and now there's only state was actually pushed onto the track frame by the processor. And the goal here again is that at some point we may want to return, although in its code it's never going to return. Yeah.
So what can have those fork rest and track that?
Ah.
That seems like such a
Okay, so we're going to do two very different things. Right? Fork ret is returns from the fork system call, basically. It's the path to get out of the fork system call. And remember that fork was special, correct? Because it returns twice. Once through the parent and once through the child. So there's something special that has to go on, must be going on, which we'll talk about a little bit later. Trapped ret is just the return out of an interrupt. Anytime you turn out an interrupt, including a system call, correct, and the x86 is an interrupt, that's the way you get out of the kernel.
so we need to take both of those.
Yeah, so we faked both of those, right? We did just, what happened with this first process, if the first process made the system call, and it called fork. And so, and the reason we do it that way is because then we can reuse all the other code that we already have for fork and all the other stuff in the kernel. There's very little special code for just init. All right? Yeah.
So CS and SS are different, which is the reason that the stack is going to like throw down and eventually override the instructions. Is that right? For at least user space.
Yes, the stack goes down and can override instructions. In fact, we'll see later.
It can.
In this case, it can't. In principle, it could. It doesn't, because it's carefully written. That the stack is big enough that and the amount of code that we have in that one page is big enough. But when we set up a real process, you'll see we'll put something in between at the bottom of the stack to make sure that actually you don't overwrite by accident your instructions or your data.
So does that mean that the two page tables that are pointed at by CS and SS, those map that to the same?
Yeah, hold that question, then we're going to talk about all that stuff. Yeah.
So how does execution return back to the scheduler and with like the boot stack in place?
So the way so the scheduler actually has its own stack, its own thread, its own thread of execution with its own stack. And if you look at the code down here, sometimes when there's a timer interrupt comes in, and the timer is run long enough, we basically context switch back to the scheduler. I can't find it right now, but we context switch back to the scheduler, and then the scheduler is going to run again and then saves. And in fact, it comes back out of switch.
Right.
And we'll talk about that in 2 weeks or a week and a half or something. When we're
So
talking
when I
about.
passed in the switch,
Yeah.
made sure that
Yeah.
like
We're going to basically, the scheduler's going to return out of that switch.
yeah. Okay.
All right? Yeah.
Are you using the page table in the process?
Yeah, we did allocate it a little bit earlier. I'll talk about it in.
Where you switch the page?
Yeah, we did it earlier because remember the reason we don't really that this is pretty straightforward is because the kernel was mapped in the same place in every process. So we didn't really, when we added this page into it, we were already running with the address space of the kernel. Oh, great questions. You keep asking questions. But this is the lecture to ask a lot of little questions because a lot of little details. And so feel free. I mean, that's the whole purpose I'm here. So, all right. Good. So this was, super exciting. We went to user space and immediately went back down to kernel space, and we're doing an exec system call. But I don't want to talk about the exec fork now because that just gets us into the whole. I'll talk a little bit, next week or something. We're going to start talking about it. Instead, first I want to talk more about the address spaces. That's back to today's lecture. Let's see where I want to start. So we actually we can maybe a reasonable place to start. We can actually look at the address space, correct, that we're actually running with. In answer maybe to your question. And this process has run now a little bit, right? So it has a bunch of states. You'll see that this is all the kernel stuff. And then the top, there was that one user page that was mapped, right? The page 0. So if we look at this picture, all these numbers, that actually corresponds to this picture. Right? There's a lot of page table entries going up from kernel days on, and then at the bottom, one page that actually maps that particular user image code. So now what I want to do is actually go in detail and describe actually how the x86 MMU hardware works. Right? So to do that, to help you along with that, I brought you a handout, probably the only handout I'll give in this class, which has all the this is sort of a cheat sheet with all the MMU information on it. It's extremely useful. You probably just want to keep it around while you're writing your JAWS code. Basically, it has in one page on the front, it has the MMU hardware, and the back it has all the special purpose registers. It's going to be extremely useful to have here in head. So remember, the picture I drew last week describing translation of the physical addresses. That's sort of this following picture. Right? The processor running. In the processor, there's loads of storage instructions to memory with some address. And it turns out that those addresses are virtual addresses. So they don't refer to a particular piece or directly indexed into physical memory. They actually happen to be an address that actually first is translated by a machine, a piece of hardware, which is called the MMU. And the MMU has a translation as a page table to translate things, and the pointer to the page table is stored in the CR3 register. And that actually, so the MMU translates virtual addresses into physical addresses. And they actually refer to an actual location in physical memory. So notice when the processor executes any instruction that has an address, right, all those addresses are virtual. Never a physical address. Every instruction only takes virtual addresses. Yeah. Sorry? Yes, sorry. When the first, well, as soon as you enable the MMU, very good point, then everything is virtual. Okay, so now if you notice, this picture is not exactly actually what the x86 does. The x86 is slightly more complicated. There's a little thing sitting between the MMU basically consists of two boxes, if you will, namely segmentation hardware and then actually page tables. We're going to ignore segmentation, and basically the way segmentation for us is going to be set up is basically it's a one-to-one mapping. So address 0 maps to address 0. Now you're going to see, yeah, does everybody have a copy of this?
Yeah, we need one more.
There's more. I was going into. I thought I had enough, unless you guys increased the number. It's also on the website. Are we good? So for the x86, because there's one more box, there's one more type of address. So there's not just virtual physical, there's one other address. So the way that actually works is the x86 refers to this address that's issued by the CPU as the logical address. The logical address goes through the segmentation hardware, and that produces a linear address. And the linear address goes through the page table hardware, and that gives you a physical address. Now, since we're setting up logical addresses to be a one-to-one mapping to linear addresses, for us there's no point in making any distinction between the two. And so we're just going to use the standard terminology of virtual address for that. Yeah? Does that make sense? You might wonder why the x86 has segmentation hardware and page table hardware. In fact, because they're both plans for actually doing isolation or different pieces of memory. And that is mostly for historical reasons. I think almost nobody or no operating system really uses the segmentation hardware or relies on the segmentation hardware in any interesting ways. There's one or two cute tricks you can do using segmentation hardware, but basically you can just forget about it. It doesn't exist. The x86 started out with having segments from the origin, right? This is why CS and whatever was there from the start. And so it was natural for them to first go through the segmentation hardware plan. And then later on, when it turned out that competitive processors like the Motorola 68000 basically were blowing them out of the water, they quickly also switched to 32 bits and incorporated page table hardware. All right. So that's mostly historic. Yeah.
Is there a reason that the processor making so much backwards compatibility? I feel like with our passwords would be so much faster if it was like screw everything before.
What do you want me to say? I'm money. I think Intel has always stuck to the philosophy that all programs should just run without having to recompile or anything. Just the binaries from the settings should still run. And so they made sure that that was the case. I think there's motive for people to transition. Now, you can argue endlessly whether this is a valuable property in today's world, but they're stuck to it. And so then there's a whole other argument about, well, could you make a processor much faster, better, if you didn't have all this baggage, right? And like the ARM processor is sort of a clean design that doesn't have all the baggage. The only thing I point out is that the x86 has been holding up pretty well, right, over 4 decades in terms of performance. So it's not clear. Maybe it will change, maybe power will change the dynamics completely, but I've written off the x86 a couple times and it never really worked out. So now I'm much more careful about my predictions. Yeah, go ahead.
Well, Intel did make the Itanium, and then no one bought that.
Oh yeah. Okay, that's actually true. Intel has designed many other processors, correct? Which some of them saw the day of light and didn't do anything in the marketplace. Some of them never really succeeded, never worked. Yeah. Now, from our just to like as a side point, correct? Even though we're sort of all into the details of the x86 processor, most of what we're talking about, or what you're exposed to in 828, is basically pretty standard stuff. The ARM has a page table. Any other processor has sort of similar type of hardware. Okay. Okay, good. So now we can talk about a little bit more detail how things work. So the process of how an address is translated is shown on the second line, and you can see that we look at the logical address. You can see there's a selector. That was the selectors that we just talked about, like the code segment selector, the data selector. It turns out those selectors are indexed into a table, which is the GDT that we've seen a couple times. We do our utmost best to ignore them, but once in a while they show up. And so it's worthwhile knowing at least once that they're basically the selectors used as an index. The index tells you what the base address is to which the 32-bit address has to be added to. And what is the base address that we're going to be using in DOS? 0, correct? So the base address is 0. And what is the limit? The limit is the end of that region of memory. And to what do we set the limit? Yeah, to top of physical memory. So basically, this thing just totally doesn't do anything for us. Right? It just translates 0 to 0 and doesn't do any checks to see if things are out of bounds. But you can imagine schemes where you would do bound checking using this limit and bound bit, but we don't do that. Okay? So basically, you can ignore the selector, and basically the 32 bits are basically coming into the page table hardware. Right? And that's where all the work that we're going to be doing, and that's what you're playing around with in the lab too. Okay? So, and you should see that, so let's look a little bit in detail how that translation actually happens. The way it'll do that is basically writing sort of equivalent C code so that you actually have an idea of what's going on. So the way the hardware, this MMU, translates a particular virtual address is it first looks in ZR3, correct, and finds the page table directory. And so that is the first instruction you see. And so often what we'll see is you see page table directory, and that's loaded, that's CR3. And what's the address in the CR3? In fact, if you want to look at on the other side of the page, there is actually the layout of the CR3 register. And you notice that there's first 12 bits on the right are flags, only 2 of them we used, and then the rest is actually a number. And it's called the base address. What is the base address? Is that a physical address or a virtual address?
Is that physical?
It's a physical address. Why does it have to be? This is a crucial, correct? Because like in lab 2, when you're setting up the kernel page table hardware, you better stick a physical address in that register. If you put a virtual address in there, something really bizarre will happen, right? And then you will interpret that virtual address that you stuck into it as a physical address, which presumably will point to some very different location in memory, and read the bits there as basically the top level page table directory. So it has to be a physical address. So the kernel actually has to do the work to actually translate those virtual addresses that it has to refer to page tables to physical addresses to store them actually in the hardware. Right? And this is where in JOS code you see everywhere minus and plus current base. Right? And we'll talk about it in a second more. Okay, so that is a physical address, and that basically points to a page of memory. So the translation on the x86 happens in 4 kilobyte pages. So you translate a complete 4 kilobyte at the same time. So you don't translate byte 1, byte 2 separately. You know, they're all, the first 4K are translated by one page table entry. Why do that? Why not like something smaller? Translate,
Because then the overhead of the page table is huge and
Yeah.
takes way too much memory.
They would try to amortize the overhead of having those page tables around, correct? And now basically you need one entry for 496 addresses. Yeah. Great.
A lot of the page tables is cached, so you can actually just keep a lot more memory, like memory.
Correct. Because the page tables need to be cached actually by the MMU, even much more efficient way of doing it than actually doing every individual entry. I'll talk a little bit more later at some point. I will show up. And so the page directory corresponds to one, the top level page. So it's a 2-level page scheme, correct? It's a tree, and the top level page directory consists of exactly one page, 496 bytes, which is 1,024 words, right? And which is why the indexes run from 0 to 1,023. Yeah? Make sense? And so the way the indexing works is you take the top level bits, the top level 10 bits. 10 bits allows you to address 2 to the power 10 is exactly 4 kilobyte, 1 kilobyte I mean, entries, and that you use as an index into the page directory. And so you see a lot of code to perform. So you take the page directory, and you index it with the top level 10 bits. And I think in the macro that we often use is PDX. Say this is the address. And that gives us a physical address of the page table. Right, so then so basically this is the first step of the process, correct? You take the top level 10 bits, index into the page table, page directory, gives you an entry. That entry is actually not the translation, and it contains another pointer to another page table. Correct? It's a 2-level scheme. And so we'll look at it in a second. And so then we use the next 10 bits to index into this is the page table entry, page table, and I think it's the PX, the macro that takes the next 10 bits out of the address and use that as an index into the page table, which then gives us a PTE, a page table entry. That make sense? So that takes the top 20 bits, and since their pages are 4 kilobytes, the next 12 bits are basically an offset in that page. Right? So the final translation step is that you add in the offset, and that will give you the actual physical address. Hold on one second. So what is stored in the PTE? What is stored in the PTE? That's the physical page number, correct? So you map virtual page numbers to physical page numbers, and the physical page number is a 20-bit thing shift to 12 bits, and so that gives you a physical address, plus the 12 bits that are sitting in your virtual address. Add them together, it gives you 32 bits, and that gives you your 32 bits physical address. Make sense? Okay. You had a question, somebody?
Yeah.
Okay, good. That's ideal. Okay, so why this complicated 2-level page table structure? Why not have one big array?
So that you need more and more page tables, you just expand this much more page tables.
Yeah, fragmentation is one reason. Any other big reasons why this is true?
It becomes a lot easier to map the same physical memory to multiple places in the virtual space because in the page directory you just point to the same page table for multiple entries.
Yeah, okay, so it's a way of doing all kinds of cool tricks, which we're going to do some of them. It's not, yeah.
Lets us potentially have a lot of mappings instead of pre-allocating ways of space.
Yeah, I mean, basically, it's space is simply matter. Like, how big so a typical process will it have 1,000 pages or 1,000,000 pages? Okay, 1,000,000 pages, correct, times 4K is 4 gigabyte. So how many processors are going to be 4 gigabyte large? Not many, right? In fact, all the processors that we've seen so far, like init code has 1 page, right? And so we allocated a complete table for mapping everything. It would be very expensive, right? And this two-level scheme allows us to avoid having to map everything. And so we can see that more clearly now if you look back at this screen. Okay, here we go. So let's look at the first. So now I can explain this better. So you'll see here, that, in fact, that the number of PDEs filled in for this particular process is very small. Right? There's only a couple entries in the top-level directory that actually are filled in. In fact, the bottom one is filled in with entry number 0. And so how many addresses are mapped by entry 0 in the page directory? Well, there are 1,024 entries in the page directory, right? So 4 gigabyte divided by 4 kilobyte, it's going to be 4 megabyte. So one entry in the PDE basically maps in principle 4 megabyte. But you'll see that actually only, and so it points to a particular page table that maps that 4 megabyte, correct? And so that is the next index in the next 10 bits. And you see, in fact, that only one entry is filled in the page table structure. Right? So on the top level, the very first entry points to a page table that has one entry into it. So we're wasting 1,023 entries in that page table, but that's all we waste. Nothing else. Because the next entry, correct, is actually on the address 256. So that's the 5 and the 12 entry in the page table directory, and that maps. And that maps from here on to the top, right? And notice that for all these mappings, we actually maintain no state whatsoever, right? There's no memory allocated to actually maintain those mappings, other than 0 entries in the PDE or the B page directory, the top level directory. Yeah.
So there are super pages, just PDEs that are mapped to a contiguous chunk?
Exactly. So this is as a side note, you will see in the PDE, there's a bit in the PDE entry that's the S bit, or that stands for super pages. And the super page is 4 megabyte in size instead of 4 kilobyte. And that makes a lot of sense, correct? Because basically that maps the complete 4 megabyte linearly without actually using an additional page table entry. So this picture is slightly wrong, if you will. This picture describes the translation for 4 kilobyte pages. But later on, the x86 added 4 megabyte pages, and this is the way they stuck them in. Any questions? All right, so let's look a little bit more. So then we'll see there's quite a number of entries, correct, in this range. So this is PDE 200. So that's the first, the 5 and 12 entry in the top level directory. And that points to a physical page that contains a page table. And that page table contains all these entries. In fact, that page table is almost completely filled out because it goes to free FF, right, which is going to be the top level entry in the page table page. Make sense? And how many of you have already been staring at these page table directories for lab 2? You will before Friday. You have to fill this out, correct, and submit it. So if you're smart, whatever, you use page info and then you copy that and then you submit that. After, of course, you got it correct. flights, shells. So this entry, correct, what does this do? This maps the first page of the kernel. And it maps it to where? To physical address 0. Right? So this is exactly that mapping from here to there. Right? Make sense? So we can poke a little bit more, and then there's a bunch of more pages mapped. And some of these entries are multiple entries, or a series of entries that maps to a sequence of continuous physical pages. But it doesn't have to be, right? Like one virtual page might map to a physical page in memory. The next virtual page might map to a totally different physical page in memory somewhere. But often you see there's a sequence, and that's because if you're doing boot up, we just allocated pages in sequence, correct? And so therefore those entries are going to be sort of similar. You see also some bits, correct? WP means that you're allowed to write to it, and you see that the second page didn't have write permissions. And that presumably is where data is stored, or read-only data or text is stored from the kernel. Okay, so that's PDE 512. Then apparently PDEs 511 to whatever, to hex 236 are also filled in. In fact, 237 is also filled in. And then it basically stops. Right? So then there's a whole bunch of entries that are basically zeros and they're not displayed by this info program. Okay? And then at the very top, there's a couple more pages that are filled in, and that is actually to map I/O devices that sit in the very top of the memory. Right? So that means this mapping. The top is mapped from here to here to physical memory. Okay? Yeah.
On 64-bit machines, do we have 26 and 26 bits worth of PD and TT?
Yeah, 64 basically adds one more level to the page table directories. But it's the same idea. It's a 3-level scheme.
But then the 52 bits is not divisible by 3.
Whatever. I don't remember exactly how the bits are cut up. I mean, clearly you can cut them up in any way you like, right?
You only get 48 bits.
You get 48 bits on 64. Currently,
You don't get to have more addresses than that.
Yeah. But they can change that, right? There's all kinds of games you can play. You know, your virtual addresses can be bigger than your physical addresses, or the other way around. And you know, over time, over the decades, you know, all those things have changed, and I'm sure it will change again. Okay. So does it all make sense? How the page table hardware works? This will be very, very important because you're going to be setting up a lot of these page tables. Right? And use this feature that we added to QEMU to actually print out the page tables in a sort of more pleasant way, so you can look at it if you see if you did it right. All right. Now, there's a couple. Now, I can ask you. Now, given this mapping, right, there's all kinds of interesting questions that we can ask. Like, why did we choose this mapping? We could choose many, many other different types of mapping. Right? Why do it this way? And so there are a couple observations. I hinted to a couple already earlier. One thing that's interesting is that both the kernel and the user text or the user programs are in the same address space, although set up in a way that the instructions that are here can't actually write here, right? Because if you look at it carefully, you will see that the view bit is not set. The U bit is only set for the bottom page. And so when you're user mode, there's only one page you can write, one virtual page, namely the first one, and no other ones. In kernel mode, you can write all the other ones too, or they translate. Okay? And so, just to why is this handy? Why is it handy to have the user code and the kernel code all in the same address space? One way to think about this is think about your homework and what you do today.
You don't have to switch the page directory when you switch from user to kernel space.
Yeah, we don't have to switch page directory when we switch from user to kernel space. Furthermore, once we're in the kernel, can we easily get to the user data structures? Yeah, we can just use virtual addresses to pick them out, correct? Which is like what arc induce and arc whatever the two call copy values from user space to the kernel space do. Right? So that's a handy. What other things are handy about this setup? Can the kernel, let's say the kernel, I said earlier, can the kernel actually easily get to physical memory? It's easier to translate virtual addresses to physical addresses. And once in a while, you have to still use the once in a while the kernel has to pretend to be the MMU, correct, and compute what the physical address is so that it can stick it into the page table hardware. Is it easy to take a virtual address and translate it into a physical address?
You just subtract kern base, right?
Yeah, you just subtract kern base. Right? So it's carefully set up to make it very easy for you. But because you have a virtual, the physical address, all physical memory is mapped correct straight from 0 to whatever to the top of physical memory from the kern base up. And so the kernel can always get at the physical address very quickly or easily by just subtracting kern base, and that gives you the physical address for that virtual address. Which is handy when you have to fill in the PDEs and the PDTs and all that stuff. And JOS does the same thing. Now the downside, correct, of this is that all physical memory is mapped into the kernel address range. So how big is this range and how big is that range? Divide exactly 2, right? So this range is 2 gigabytes, this range is 2 gigabytes. So can this design have a machine with more than 2 gigabytes of physical memory?
You won't be able to use it.
Yeah, you won't, yeah, I guess that's a good point to put it. You can have it, but you can't use it. Right? You can only use, because it only maps the first 2 gigabytes of physical memory. It's the only way the kernel knows about it, and it doesn't have another way of referring to more than 2 gigabytes of physical memory. Does that make sense? So this is the downside of this scheme, is this mapping is simple from physical to virtual, but the downside of it is that all physical memory is actually mapped into the kernel's address space, which limits the kernel's address space size. How about the user process? How big can it be? Also 2 gigs, right? No more than 2 gigs, because the only else the rest is already taken up. That part of the address space is already taken up by the kernel empire. Yeah.
But you could have multiple processes that, like, say, if you're demo like text process, then that could still use all the 4 weeks.
Yeah, you could have multiple user processes, but per user process, there's no more than 2. A user process cannot be bigger than 2 gigabytes, right? Yeah.
So I'm confused. If you have multiple different, is the top kernel mapping, is that always mapped for each process?
Yeah, the top level mapping is always mapped for each process. Right? And we do that so that it simplifies our lives.
So that every single process has its own, all the kernel mappings is all mapped to
yeah. It's all the same.
They all have different mappings.
No, they're all the same. This is designed basically for simplicity for OS designers, not for user programmers. Right? Same as in JOS, make it easier to life for kernel developer, not for let me hold on for a second. I'll get you this next. So this is also limited to 2 gigabytes, right? Which is a little bit of it's something like if you were Linux, this would be a bummer. You should be Linux kernel. We want to do better than that. You want to be able, if there's more than 2 gigabytes, you want to get more than 2 gigabytes user process. So what is that easy to fix in our current design? For example, one thing you might think is like, okay, well, I want more than 2 gigabytes. I just raise, the kern base a bit up. Would that work? I think it works. People think it's not working. Do you think it works?
Yes.
I want. Not that easy though. Actually, it doesn't really work, right? Because if you move this up, right, then the kernel can't actually address anymore, the top part of the 2 gigabyte physical range. So if you just move up with 1 gigabyte, right, it means that the kernel only meant 1 gigabyte of physical memory, and the kernel can only manipulate that 1 gigabyte because the rest of it doesn't show up in its address space. So actually, this boundary is carefully chosen and basically limits everything to 2 gigabytes. Does that make sense? One other interesting feature to sort of point out with this piece of code is that some physical memory is mapped twice. And there's another trick you can play with virtual memory, and we'll talk a lot more about Wednesday, but some piece of physical memory is mapped twice. For example, init code, correct? That piece of physical memory, the physical page that holds that set of instructions is mapped into the user part of the address space, and of course it's mapped into the kernel part of the address space because the kernel is able to refer to any piece of physical memory. You see? Okay, so this gives you a little bit of a sense why the layout. The layout is not arbitrary. was sort of some thought went into to figure out what to do. And as a kernel designer, you can play games, right? You can decide how to set up your address spaces. And you will see that the JOS address space is set up slightly different, although also very much in a similar style, basically designed for simplicity. So just as one experiment, let's say we do want to, we're like Linux kernel developers, and we want to have a user process allow a user process to have more than 2 GB of memory. How do we go about doing that?
So instead of always having the kernel mapped, we would only have a very small portion, perhaps just one page, that would just trampoline us into the kernel. So when you want to do something like a system call, you jump to that trampoline, you set up the page table so that you remap the kernel, swap out parts of the user process, and then jump into the kernel. Now, the problem there is if you want to write into user space, for example, some result of a system call, you need to make sure that you don't unmap the portion of the virtual memory space of that process that holds the pointer that you're trying to write to. So there's a little bit of achiness there, but
So let me sort of paraphrase this and slightly make another observation that's directly related to making it easier observation. There's no real reason for the kernel that it actually has to map the full 2 GB of physical memory. One doesn't need it. One doesn't need to refer to those physical memory locations. And really need the full 2 GB. It only needs the space that's necessary for the kernel text and data. The rest it doesn't really care about. The only reason we have them mapped in is so that you can easily fill in those damn PDEs and PDTs, correct? Because those require physical addresses, and we want to, and they be referenced by physical addresses, so it's easier for you to manipulate them that way. But what we could do, whenever time we need to refer to some particular piece of physical memory, right? What we that point, the kernel will just decide, all right, I want to write over that particular piece of physical memory. Well, I'm going to map it into my page table, set up the page table, modify the page table, load it in CR3, do the work necessary, and then unmap that page. And so in principle, the kernel could manipulate all physical memory with one page, by just unmapping and man-mapping it every time. And that will allow us to not have to, then the kernel doesn't have to be the full 2 GB, correct? It can be just whatever is necessary for the kernel itself to run, which is the size of its text and its data structures. Does that make sense? So if you're all excited about it in Josh, you could try to make that happen. And it turns out a little bit tricky, because even when you go from kernel to user space, you have to be, if you really want to set it up right, you have to be very, very careful. Does everybody see that this is, basically this is very simple for you, but I guess a pain in the neck for user processes that are bigger than 2 GB, they can't run. Okay? Okay, so let's see a little bit there. I think we have a little bit of an understanding of how the hardware works, correct? Why the mappings are set up in the way it is, and that typically when you look at an operating system, whether it's JOS or x86 or Linux, one of the first questions you're asked, okay, how is the virtual address space laid out? Right? And you can look at it and then argue about it whether it's a good design or a bad design or whatever. Okay? So let's go and do another. So understand a little bit better how all this stuff works. And the way we're going to do it is by looking at how a program or a user level process can grow its address space. So let's say, if there's user address space, we want more memory than just this one physical page. And we have to ask the kernel to grow its address space, correct? So it can use more memory. The Unix system call for, the old way for doing that is called sbreak. It allows you to basically grow your address space. And so we're going to look at quickly how sbreak is implemented. Because really what needs to be happening is, physical pages need to be allocated, PDEs need to be filled in, and all that stuff, right? And that's going to be useful for you when get a better understanding of actually how the hardware works. So we'll start over again. Good. And I'm going to set a breakpoint at sys. Continue. Should give me a shell, correct? Because nobody's asked for any memory. But it turns out any command that you run under xvsig, one of the first things that it's going to do is actually allocate memory. And the reason is that the shell, if you remember, well, it's a little bit hard to remember, but the shell, before it actually runs a program, it actually allocates mallocs and argument structure. And so it calls malloc, and the first thing the malloc does is actually needs memory, so it calls sbreak to actually get memory. So if I run ls, you see it calls malloc, I put some print statements in to see that, it calls more core, which is in umalloc.c, and that actually breaks points into the kernel, right? So this is, you all now know from your homework, right? This is like get the argument, and we can see, I guess we can print n, and we can see how much memory malloc allocates by default. So it's going to allocate 32 kilobyte of memory, or it's asking the kernel, please give me 32 kilobyte of memory, or more particularly, it asks, can you extend my address space by 32 kilobyte? Okay, so we're going to go in. Oops, that's not exactly what I wanted. I'll run another program. I'll break again there. And hopefully this time around I won't. Stuff. So now I'm grow proc, correct? And then we're going to grow the address space. First, it's going to do some checks to see what actually it's growing or shrinking the address space. So it's growing in this case, so we're going to allocate some more memory. So the first thing it's going to do is call this routine called allocupm, passing in the page directory, the top level page directory, and the current size, which is the current size of the process, in size plus n. Okay? So before sort of jumping all the way too deep, let's actually look at the page tables before we do anything. And so we really want to focus on the first entries, right? We already have entries 1, 2, 3, and 4, or 0, 1, 2, and 3. And presumably what's going to happen as this result of this process is that we're going to allocate a couple more entries. In fact, we need to allocate, we're going to grow the address space by 32 kilobytes. So how many more pages do we expect to show up? 8, right? 8 more entries need to be filled in. So let's walk into that function. It does some checking. It actually checks if new size is bigger than current base. Why is that checked there? Yeah.
So you don't exceed 2 gigs of memory.
Yeah, we want to double check that the user program is actually not extending 2 gig, because if it did, it's going to start writing over kernel. You can't allocate kernel space to it or memory to it. Right? So it's just a safety check. See if it's all big enough. If not, basically it's going to round up the old size to something to the next 4 kilobytes, correct? And the reason we do that is because everything is at a 4 kilobyte range, or units, so we have to be a little bit careful. So then it's going to go into the loop and basically allocate, fill in, hopefully PDEs for us. So let's see what actually happens. So it's going to allocate a physical page, correct? That's going to be mapped. That's the goal of that. We allocated some physical page that we're going to map into the user space region. We're first going to check actually if we succeeded. If mem is 0 means that the kernel is out of memory, and of course we can't do anything anymore at that point. And we zero the page, and then here's all the interesting stuff happening. Here's where actually we're going to map that page in, correct? So we have some address for memory. That's where the physical page is located. But the memory itself, correct, is a virtual address. And to map it in, we need actually the corresponding physical address of that page. So the V2P translates the virtual to physical page. And that's very simple, correct, because it's just minus current base. In the same way it will work in your Josh. So we're going to single step into that. So here's map pages, correct? It takes a couple of the page directories, the top level page directory, virtual address, size, physical address, etc. So it's going to round, oops. It's going to round things up, and then it needs to find the PTE, right? And then some of you probably have been looking at this code for JOS. It's actually very similar code. Not surprising, because basically walk page there literally implements the, basically it's the software version of the MMU. The kernel is just pretending to be the MMU because it needs to set things up, and so it needs to actually walk down the user space directories, or the 2 levels, to find out which PTE it then needs to modify to actually record this particular new physical page. Does that make sense? Okay, so let's walk into this and see actually how it works. And we will see this is very similar to the code that I have on the right here, or on the board. So it takes the top level 10 bits and indexes into the page directory, correct? And that corresponds to indexing in this top level page. And then it takes and then the first thing it does is actually checks if actually if the present bit is set. What is that? Why does it do that? Yeah, it just checks if there is a mapping. If the present bit is not set, there is no mapping. If the present bit is set, there presumably is a mapping. Right? The kernel has set it up earlier. So we'll see what happens here. Apparently there was a mapping, and now we're going to actually find the corresponding. So there was a physical page. The page table was already allocated. Right? So the second level was allocated, but now we need to find the entry in the second level that we need to modify. So we'll take the next 10 bits, right, of the address, and use that to actually find the page table. So next room, and we then return that, and that's basically our entry to the PTE. Right? So what we'll return is a pointer to the PTE that we need to fill in. Right? And now we can check if that PTE was already filled in. If it already was filled in, we don't have to do anything. What is our guess? Do we think that that'll be actually, if it already was mapped, something was really bad when it happened, and so we basically panicked. It means that we made a bug. So the right thing that happened shouldn't be mapped at all because we're about to fill it in. Right? So now we're going to, here we're filling it in. Right? We're taking the physical address for that map page that we allocated. We'll stick it in the PTE. We set the permission bets, and we set the PTE, the present bit. And then, presumably this instruction actually writes and actually fills in one PTE entry. Does that make sense? Now we can look, right, quickly and see. Oops, maybe we're lucky, and because actually we're modifying the current page table, correct? And the hardware is running with that page table. So we modified an existing page table as it's being used. And so maybe actually if we look at what the hardware has seen, maybe we'll see our page. And let's see if we're lucky. And we got our 5th page, correct? So suddenly we have another PTE filled in, and it actually points to this physical page. Make sense? Now, the reason that we can see this is because we're running on the QEMU. The real hardware, you can't have the hardware print out the page tables, please. But the QEMU we can. Actually, in reality, it is not the case that when you update a page table, that's guaranteed that the hardware actually immediately will see that translation. In fact, you have to, on the x86, what you will see later, you will actually have to load the CR3, and that basically indicates to the hardware to reload the page tables. Okay? So normally, to make an entry changing the page table visible to the processor or to the MMU, you have to reload the CR3 that tells the MMU, oh, I got to fetch the page tables. Yeah.
Is that because of the TLB, or is that?
Yeah.
Okay.
So basically, the MMU, the short answer is, the reason is that the MMU caches those pages, frequently used pages. So that's called the translation, and that cache is called the translation leukocyte buffer. So basically, the way to think about it is you just take these page table directories and these page table tables and just caches them inside the MMU. Performance. Otherwise, you have to go fetch them first, then load them, do the translation, and then actually get the address. Yeah.
So that means effectively, if you don't make some changes to your entry, you don't realize you're free, you might or might not get the new stuff.
Yeah.
It's probably unpredictable.
Yeah, exactly. Unpredictable. Yeah. Ideal. You can imagine making great bugs that really happens. Yeah. Luckily for you, we make it very easy to check, right? Because you're running a QEMU, and the real hardware, you really have to get that right. Yeah.
So then also, if you reload CR3, you'll have to get everything new. It's like you'll lose all your cache.
It doesn't. It can compare, correct? If you wanted to see which ones to change. But like conceptually, yes, it loses all its cache and translates it. Make sense? And just for fun, we can of course print the PTE here too, correct, and sort of look at it. And we'll see here that actually that's the PD entry. Now, does this make sense, this PD entry? All right, well, let's look at that. So, huh?
You do it slash P, so you can see the binary.
Oh, you want to see the binary?
Well,
Okay.
maybe it makes more sense.
I guess I'm so good at reading X. Oops. Is it?
X.
Slash, that could be slash PTE, like this?
Slash C is, I think, a size, not binary.
And then,
I don't know what.
Not the star.
All right, well, you know, you got to read hex. Me. It actually is pretty easy, correct, to do hex because every digit corresponds to 4 bits. And so it's a pretty straightforward translation. By the way, anytime you need to compute anything, correct, from hex to anything else, for example, you want to know what hex 200 refers to, you just do it by GDB, correct? So you don't have to think hard. So GDB is great for this, like converting numbers back and forth and all that kind of stuff. Don't do it on paper, let GDB do the work for you. Okay? So let's look at this PDE, this PTE. This is a PTE entry, correct? It's in the page table. So what is these are the bottom, since this is hex, correct? These are the bottom level, the bottom 12 bits, right? Because every digit corresponds to 4 bits. 3 of them correspond to 12 bits. So now we can look at them, correct? And look at the PTE entry and see what after the bits are set. So apparently it's 7, correct? Which is 3 ones. So the bottom 3 bits are set. Right? Does that make sense? And so that's U, W, and P. So it means the page is present, it's writable, and it's writable by user programs from user space. And this is exactly what we want, correct? Because we allocated the new page of memory for it to be used by a user program. Make sense? And then the next 20 bits, correct, are going to be the physical page number. D7, whatever, 76, correct? And that's exactly what we saw actually in the page info structure. Does that make sense? So that points to some, that's, if we appended more 12 bits and shifted around, that will point to some actual location of physical memory where that needs to be located. Okay? So you're going to be doing a lot of these manipulations with PTEs and writing code that sets this all up, hopefully correctly. But the first time you're going to get it wrong, and then it's going to be really weird bugs. Right? Does that make sense? That your bugs are going to be really strange when you get your translations wrong. Good. Because the rest of the loop is boring, correct? Because basically it does it 5 more times, or whatever, 7 more times, and before it finishes and then returns to user space. So I'm just going to skip that part. Basically, filling A.11 is the most crucial part in terms of understanding what's going on. Any questions about this? Yeah.
So after you change your page table and you load CR3 to tell the MMU that you updated the
Yeah.
page table, like what if like you make some mistake at the page table and it's like now formed? Will the MMU like somehow like alert you like, oh, there's a problem?
Yeah, well, okay, so in general, okay, so in fact, what happens if you access a page where, for example, the P bit is not set in the page table? Yeah? Yeah, you get a page fault. Right? And so what is a page fault? Page fault is like int, like a system call almost. And basically, translate, push the processor back into some other set of instructions. You re-enter the kernel basically at some other point, and then the kernel can look at this page fault and actually do something interesting with it. So in fact, what you're going to be doing for your homework for Wednesday is pretty cool. S-break is like the old way of doing things, allocating memory. What you're going to be doing is like this user program that wants more memory, it's just going to reference an address above its address space. That will result in a page fault that the kernel will get. And your job is basically the page fault handler to allocate a new piece of physical memory and actually fill in the PDE and then restart the instruction. And that way your address space grows. Okay? So this is one of the many, many cool tricks that you can do once you have virtual memory. And so in fact, Wednesday's lecture is all going to be about tricks with virtual memory. Review will do a lot of it also in JOS. We're going to do copy and write in JOS. We're going to do PPTs in JOS, like all kinds of cool VM tricks. And they're very useful. So in fact, for Wednesday, your assignment is basically to do the same thing as break, but in a page fault template. So it's a little bit more complicated than the homework for today. The homework for today, I think, was hopefully pretty straightforward. And so this one is slightly more complicated, and also you can get it really wrong, right? And then bad things happen. On the other hand, you don't have to read any code. There's nothing else to do other than that one homework, so it should be cool. And it's a good thing to do because we're going to do similar things later on in JOS. So it's nice to sort of explore this in a more constrained, wider version. Okay. Any questions? Then on Wednesday, I'm going to I'll show you the solution for allocating the homework, and also we'll talk about a bunch of other tricks using virtual memory. All right.